we're going to consider higher order linear differential equations. So in general, a higher order equation looks like this. You've got some functions of the variable in front. It could be anything, polynomials, constants, exponentials. And then each of the derivatives and of the function and the function itself only appear linearly. Those are all examples of them, and we want to know, well, how do we solve them? And I think the simplest thing to say is to try the same thing. And that will only apply for a constant coefficient, dE. As a very simple example, let's say y triple prime plus y prime is 0. We're going to let y equal e to the lambda t. If you assume that's the form of the solution, and you start taking all its derivatives, the chain rule just keeps giving you these factors of lambda. You put them all in, you're going to end up with an equation that looks something similar to what we've seen before. And remember, the e to the lambda t is a factor that just essentially cancels out because it can never be 0. And that means we get this polynomial equation. The differential equation was order 3. 3 was the highest derivative we had, and so it's no surprise then that the characteristic equation is a third degree polynomial. That's going to happen if you have an nth degree differential equation, an nth order differential equation, you're always going to get an nth degree polynomial. Those can be tricky to solve. Sometimes they don't have to be. So for example, this one can be solved by factoring and by using complex numbers. We can write this as lambda plus I, lambda minus I is 0. So we get 3 solutions, 0, negative I, positive I. And that means that the general solution will just be a linear combination of these 3. C1 e to the 0t, C2 e to the it, C3 e to the negative it. Now remember, we don't like to leave things in this form. E to the 0 is just 1, so this would be C1 times 1. And remember, for these complex exponentials, we can always use Euler's formula to write them as cos t plus I sine t, and then we can group together all the coses and sines. So at the end of the day, we always just collapse this down immediately to the sine cosine basis. So the general solution here would just look like this. So it worked out, at least for this particular example. So the theoretical results for higher order dEs are the same as for second order dEs. Now on the attached sheet, I've written this out more precisely, but there's theorem 2.3.1, an nth order IVP has a unique solution. So if you start with an nth order differential equation and you give it the right number and type of initial conditions, it will always have a single solution. And just like we did for the second order case, you can piggyback and show an nth order differential equation, so an nth order linear dE always has a fundamental set of n solutions. So a third order dE must have a basis or a fundamental set of 3 solutions. A 17th order dE must have a basis of 17 solutions. And you can always write the general solution as C1y1, C2y2, all the way down to Cnyn. So everything ends up being exactly the same in terms of what we expect as it was for the second order case. The issue in solving higher order constant coefficient DEs is really how do you deal with that nth degree polynomial equation? Lots of things can go wrong, like, for example, you could have difficulty factoring it. So this will require things like the rational roots theorem. What do we do with higher degree repeated roots? And what happens when we have equations with high degree complex roots? So we'll only talk about the repeated roots case here, and we'll talk about it very quickly through two examples. So for example, if we have this fifth order constant coefficient differential equation, we know that, all right, we should always try y is e to the lambda t. Repeated use of the chain rule is just going to bring in an additional factor of lambda. Once we sub this all in, we're going to get a characteristic equation that mirrors the original differential equation, and it becomes a fifth degree algebra problem. Now, in general, a fifth degree algebra problem could be really hard to solve, but we're lucky here that this has been doctored and we can factor it. And the idea is that lambda plus 5 is what we should be looking for. If we group the first two terms, we'll have a lambda plus 5. If we group the next two terms, a common factor will be 2 lambda squared, and when we take it out, we'll get a lambda plus 5, and we'll have another lambda plus 5. So the common factor becomes lambda plus 5. We'll have a lambda squared minus 2, lambda to the 4, lambda minus 2 lambda squared plus 1 is 0. This could be factored into lambda plus 5, lambda squared minus 1 squared. Lambda plus 5, lambda minus 1, all squared, lambda plus 1, all squared is 0. So the solutions will be negative 5, 1, 1, negative 1, negative 1. The general solution will be y of t is c1 e to the negative 5t, c2 e to the lambda t, which is 1t. Now, every time we have a repeat, we know from before that we should be adding a factor of t in the front, so t e to the lambda t. Same thing is going to happen for the negative root. So we'll have e to the negative t and t e to the negative t. And there is our fifth order equation that has 5 roots. So there's no issue there. Now, what if our DE has higher repeats? So let's suppose a 7th order DE gives the 7th degree equation like this. Let's say we're very lucky and it goes lambda plus 1 cubed and lambda minus 3 to the power of 4 is 0. Negative 1, negative 1, negative 1, 3, 3, 3, 3. For each repetition, we add a fundamental solution with an increasing power of t. We increase by 1. We increase the degree by 1 for each repeat. And so what I mean there is the general solution is going to be c1 e to the minus t, c2 t e to the minus t, c3 t squared e to the minus t to deal with the 3 repeats there. And for the other terms, c4 e to the 3t, c5 t e to the 3t, c6 t squared e to the 3t, and c7 t cubed e to the 3t. So if lambda repeats n times, we need e to the lambda, e to the t, e to the lambda t, all the way up till t to the n minus 1, e to the lambda t. So that process will allow us to incorporate all of the correct linearly independent solutions into our problem. For example, if I have lambda to the 5 plus 2 lambda cubed plus lambda is 0. This could be factored as lambda squared plus 1 squared is 0. So lambda is 0, I, negative I, negative I. The general solution will be C1 e to the 0t, C2 cos t, plus C3 t cos t, plus C4 sine t, plus C5 t sine t. Now remember, e to the 0 is just a 1, so we would call that C1.